Each Hypatia railway train has one engine car followed by some boxcars in a straight line. The distance between consecutive boxes is 2 meters. The distance between the engine car and the first boxcar is also 2 meters. The engine car is 26 meters in length, and each boxcar is 15 meters in length. The total length of the train is the distance from the front of the engine car to the end of the last boxcar. What is the total length of the train with 10 boxcars? So first you have this engine, I guess. We'll just call it E for engine. And then you've got some space here. And then you have these boxcars, B, B, and so on. So dot, 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 and then the last B. So the distance would basically be the first engine, which is 26, and then the space here, which is 2, and then the total number of boxcars, which in this case is 10. So 10 boxcars times the length of each boxcar, which I believe is 15, is it? Yeah, 15. And then, of course, you can't forget about the spaces, right? These little spaces. And if there's 10 boxcars, there'll be 9 spaces. So just be careful there that you don't put 10 spaces. And each space, I believe, is 2 meters if you read the question. So there you go. That's the calculation. 26 plus 2 plus the 10 times 15 and 9 times 2. And then when you do that math, it's 196. A train has a total of 2015 meters. How many boxcars does the train have? So this time, they've given you the actual length, and you have to figure out the number of boxcars. So really just looking at that, I think it's going to be the same thing. You'll have 26 for the engine, then the 2 meters between the engine and the first boxcar. And then you have, this time we don't know how many boxcars, so I'm going to put X there, and each of those is 15. And then this number is X minus 1, and then that's times 2. And that is your equation. And I will let you solve that. I'm sure you can. And when you do, you get X equal to 117. In the diagram, a southbound train with 14 boxcars crosses the border between Canada and the United States at a speed of 1.6 meters per second. Determine the length of time in seconds during which a portion of the train is in Canada and a portion is in the United States at the same time. Well, we're going to use this formula, speed equals distance over time, famous formula, and we are given that the speed is 1.6 meters per second, and the time is what we have to figure out, and the distance is something we can figure out, I guess, with this piece of information that there's 14 boxcars. So very similar to what we did previously, 26 plus 2 plus the 14 boxcars, 15 meters for each, plus 13 spaces and 2 meters for each. And when you do this, it's 264. So now we just have to solve for t. So t is d over s, and then d is 264, s is 1.6, and when you do this math, you get 165 seconds. So for 165 seconds, a part of this train will be both in the US and in Canada. And then after 165 seconds, it will be entirely in the United States. In the questions below, A, B, M, N, P, Q, and R are non-zero digits. A 2-digit positive integer AB equals 10A plus B. For example, 37 is equal to 10 times 3 plus 7. If AB minus B is 72, what is the positive integer AB? Okay, so AB minus BA is 72. So according to their little definition, it'll be 10A plus B for that guy. And then this one will be 10B plus A. And that's equal to 72. So when you do this algebra here, you get, I believe, 9A minus 9B is 72. Factor out the 9, or divide through by 9, and you'll get 72 divided by 9, which I believe is 8. So we need 2 digits that, when you subtract them, will equal 8. And remember, they're non-zero, so neither of them can be a 0. And the only 2 digits I can think of are 9 and 1. Those are the only 2 that, if you subtracted them, would give you 8. So that means that the AB is 91, that number that they are asking about. A 2-digit positive integer mn is given, explain why it is not possible that mn minus nm is 80. Okay, so the same story, I think, pretty much. So I might as well just do it up here, keep this in the same page. So pretty much the same thing that we did before, and the only difference this time is that this number is 80. And the letters are different, but it doesn't really matter that the letters are different. Okay, so same thing, 10m plus n, and then we have minus 10n plus m is 80. And then this math brings you down to 9m minus 9n is 80. And then when you divide through by 8, you get m minus n is 80 over 9, which is a decimal. It's like 8.9 or something approximately. Now, we just have to explain in words why this is not possible, because both, as it says in the question, m and n are digits. They're numbers. And therefore, the difference between two integers cannot be a decimal. The difference between two integers is always going to be an integer. So I just explained that in words, and that should be good enough. A 3-digit positive integer, PQR, equals 100p plus 10q plus r. If p is greater than r, determine the number of possible values of PQR minus RQP. All right. So same kind of story, PQR minus RQP, and then we just again use the same definition that they were giving up there. So this would be 100p plus 10q plus r, and then this would be 100r plus 10q plus p. And then when you subtract all those guys, you just end up with 99p minus 99r. The q's cancel, interestingly. And then when you factor out the 99, you'll get 99 times p minus r. So they're basically saying, what possible values can you get? All right, well, I guess I just have to make a table and see. Okay, so let's see here. We got p. We have r, we have p minus r, and then we have the 99 times p minus r. And then let's see what we get for these values. Okay. All right, so, and then of course keeping in mind that p is greater than r. That's very important. Otherwise we'll get probably the wrong answer. So I'm going to start with the smallest, which is 2, and then that means r can only be 1. Then p minus r would be 1, and then therefore this would be 99. So I think I've exhausted the p equals 2. Let's try p equals 3. I can have 1, or I can have 2. So if I have 3 and 1, that's going to be 2. This is going to be 198, and this is going to be 1 and 99 again. Let's try 4. 4, we'll have 4, 1, 4, 2, and 4, 3. All right, so this is going to be 3, 2, and 1. This will be 297, 198, and 99. So I see a pattern here, basically just multiples of 99. And my question is, how far do we go? I think a dot, 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 all the way up to the largest p can be, of course, is 9. So if we have 9, it will be 9, 1, 9, 2, 9, 3, and so on, all the way up till 9, 8. So let's see what we get for these guys, and I should be able to make a conclusion based on that. So this will be 8, 7, 6, and 1. This will be 99. I didn't do all of them. I just wanted to get an idea. This is 594. This is 693, and this is 792. So basically, the highest it gets is 792, and the lowest is 99, and they're all multiples of 99. So my values are 99, basically all multiples of 99, 297, 396, 495, 594, 693, and 792. So that is 1, 2, 3, 4, 5, 6, 7, 8. So 8 is really what they're asking for. And I think that completes this question. Consider a line, n line segments where each pair of line segments intersect at different point and not an endpoint of any of the n line segments. Let Tn be the sum of the number of intersection points and the number of endpoints of the line segments. For example, T1 is 2, T2 is 5. The diagram below illustrates that T3 is 9. What do T4 and T5 equal? So first let's talk about this question, explain it a little bit. Tn is talking about the number of intersection points, so I'll just call it IP, intersection points, plus the number of endpoints, EP. So let's talk about it, this diagram right here. First of all, let's talk about the endpoints. That's the easiest. So here's 1, 2, here's another 2, and here's another 2. So that's pretty straightforward. If the number of, if there's n lines, right, there's going to be 2n endpoints because each line has 2 endpoints. So that's pretty straightforward. Now, the intersection points is not as straightforward. So that's what we need to talk about. That's actually a little bit longer of an explanation, but it's okay. Let's just look at this diagram. We have 1, 2, 3 intersection points. So for this particular case, it's 3. So if you count them all, T3, with 3 lines, we have 3 intersection points plus 6 endpoints, and that's how they got this 9. But we want sort of a general number, in terms of n. So how do you get that? So that's what I wanted to talk about. Now, the first thing is, let's just calculate T4 here. And when I calculate T4, you might be able to get somewhat of an idea. So let's draw in a 4th line in here that crosses everything. So I'll just put something like that. That works, right? Okay, so that worked. So now I can figure out T4. Let's see, T4 is equal to, well, it seems to me that everything that I have already circled is going to be part of T4's calculation, right? That's just because I've already circled all these in red, 9 points, right? So I think it's going to be T3 plus something. And that plus something is really what is the key. The first plus, of course, is the endpoints, and this green line has 2 endpoints. And the next plus is the new intersections. Now, since my green line is crossing the 3 previous lines, there's going to be 3 new intersection points. So I'll put a 3 there. And that is how you do it. So this will be 9 plus 5, which of course is 14. So T4 is 14. Let's do the same principle for T5. And since I have my formula, I don't need to draw in another line in this diagram and mess it up. So I'll just do T5. T5 looks to me like it'll be T4, all the intersection points that I already have, plus 2 additional endpoints for that 5th line, plus the fact that it's going to cross the existing 4 lines. So there's going to be 4 more new intersection points. So this is going to be 14 plus 6, which of course is 20. So that is the pattern. So it looks to me like up here, I have to come up with some sort of formula. And I think this system probably doesn't work as well. So I'm going to try to come up with a different system based on what I've got here and here. It looks to me like Tn plus 1 is equal to Tn and then plus 2 new endpoints, right? So I'll just put in a 2 there, I guess. So like this. And then plus, let's see here, plus n, I believe. Yeah. I think this works out. This formula would check out. Okay, another way of doing it is starting with Tn, and then this would be Tn minus 1 plus 2 plus n minus 1. So either of these are correct, I think. All right, so that takes care of A. Now let's move on to B. Express T Tn minus Tn minus 1 in terms of n. Okay, so I think that's where this one comes into play. So if I just have to bring it over to get what they have, and that's going to leave me with 1 plus n. Is that right? Yeah, that's it. And I think this holds true only when n is greater than or equal to 2. And I think that's it for this guy. That's all they wanted, really. So it's n plus 1. Okay, determine all possible values of n such that Tn is 2015. Okay. So this one, oh boy, I think I'm going to have to get some sort of a formula here. Okay, so let me make a table, because I've got to come up with a formula here. So let's see what I can do. Let's make a table n, and then Tn, and then we'll take it from there. And then Tn is this guy here. So it's Tn minus 1 plus n plus 1 when you do the algebra there. Okay, so let's make this table and see if we get any kind of a pattern. So 2, 3, 4, 5, 6, 7, 8, and so on. I think I should be able to get a pattern by the time I get to 8. Okay, so this is T2, which I believe is T1 plus 3. So that's going to be, what was T1 again? T1 was 2, right? So this is 5. And then continuing, T3 would be T2 plus 4. So that's 5 plus 4, which is 9. And then T4 is T3 plus 5, which is 14. And so on. And you guys get the idea. This is going to be 20. And you can do the math yourself. 27, 35, 44. So it looks like there's a somewhat of a standard pattern here. Like this has increased by 4. This has increased by 5. From 14 to 20, that is an increase of 6. This is an increase of 7. This is an increase of 8. And this was an increase of 9. So that leads me to think that a general conclusion is that T of n would be, what was T1 again? T1 was 2, right? This guy here was 2. So that makes me think that Tn is 2 plus 3 plus 4 plus 5 plus ... all the way up to, let's see, this was 8. If n is 8, it's 44. So it would be all the way up to n plus 1. Yeah. Yeah, I'm pretty sure that's how it works. And you can verify that by looking at any of these values, I guess. Okay, so that's a pretty good conclusion I came to, I think. So if I take this 1 here and put it out front, it becomes 1 plus 2 plus 3 plus 4 plus 5 ... all the way to n, and then another n. Now the good news there is that these guys, some of you know what that formula is, can be written as a formula n times n plus 1 over 2, basically the sum of the first n consecutive integers. And then we don't forget about this n here sticking out front. Okay, so now I have a formula. And then we want t and n to equal 2015 here. So we want this t and n to equal 2015. Okay, so now I can solve for n. Okay, without the formula, I couldn't. Okay, so now that we have it, let's proceed. First, let's multiply through by 2. And when I do, I get 4030. And this will be n times n plus 1 plus 2n. Let's put it all on one side. Let's collect like terms, all that stuff. N squared plus 3n, I believe, and then minus 4030 is 0. And I think this factors, believe it or not, 62 and 65. Negative, positive. And therefore n is 62, since n has to be a positive number, because n represents the number of lines. And I think that's the only solution. So there you go. Let GCDAB represent the greatest common divisor of the two positive integers a and b. For example, GCD 1845 is 9, since 9 is the largest positive integer that divides both 18 and 45. The function p and n is defined to equal the sum of the n greatest common divisors, GCD 1n, GCD 2n, all the way up to GCD nn. For example, P6 is GCD 16, GCD 26, all the way up to GCD 66, which is 1 plus 2, plus 3 plus 2, plus 1 plus 6, which is 15. What is the value of P125? Okay, well, let's explain this first. First of all, let's explain very briefly GCD. And some of you know this, some of you don't, but let's just say I have 2 to the power of 1, 3 to the power of 2, 3 to the power of 1, 5 to the power of 2. I broke them up into prime factors for a reason, because that's the easiest way of doing greatest common divisor. When you do greatest common divisor, you actually think smallest. And I'll explain what I mean. Greatest common divisor, you think smallest. I know it sounds a bit paradoxical, but that's how it is. What that means is you look at the smallest power of each prime number. So for 2, what is the smallest power? Well, in here, the power is 1, but here, there is no 2. So the smallest power of 2 is actually 0. Then look at the next prime number, which is 3. The smallest power is 1, because here you have 3 to the power of 2, but here you have 3 to the power of 1. And then for 5, the smallest power, well, here it's 2, but here there is no 5. So the smallest power of 5 is 0. So of all the prime numbers involved, you always just look at the smallest power, and therefore this is just 3. So the greatest common divisor of those two numbers is 3. And that's the largest positive integer that divides both 2 times 3 to the power of 2 and 3 times 5 to the power of 2. So that's a very basic introduction. So they're building on that. They're saying that we've got this definition here. Okay? So they want you to figure out P125. So what that basically means is that you want the GCD of 125 plus the GCD of 125, right? All the way ... until you get the GCD of 125. Okay. Well, that's a lot. So obviously I'm not going to do 125 GCDs, but we can think about a pattern. And what I'll do is I make a little table. The number, the GCD, and the total. And of course, there's a few categories, and hopefully this will make a lot of sense once it's all done. And then you will become an expert and be able to solve parts B, C, and D of this question. So here we go. If the number is a non-multiple, so non-multiple of 5. So for example, 1, 2, 3. How many of those are there, first of all? Well, multiples of 5 is like 5, 10, 15, 20, ... all the way to 125. And I believe there are 125 divided by 5, which is 25 of them. And since we have numbers 1 to 125, and 25 of them are multiples of 5, that means there will be 100 numbers that are non-multiples of 5. Now, multiples of 5, so multiples of 5, and then multiples of 25, and then multiples of 125. Those are the other categories. Okay, so multiples of 125, well, there's only one number, 125, so there's only one of those guys. Multiples of 25, there's 25, 50, 75, 100, so there's 4 of those, because I do not want to count 125 because that will be counting doubles. And multiples of 5, again, unique, I guess I should put in the word unique multiples of 5. Well, in total there was 25, but I already included this 4 and this 1, so that leaves 20. Okay, so now that we have that, now let's figure out the GCD. The good news is that all the GCDs will be the same for each of these categories. So you just have to figure out one. So one non-multiple of 5 is 1. So the GCD of 1 and 125 is 1. I'll just put that as 1. So just put that there. And any other similar GCD, like for example, if you had GCD of whatever, 7 and 125, 7 is a non-multiple of 5, that's also 1. So since we have 100 of these guys, the total is 100 when you add them up, because remember, you're adding all these guys. Got it? Okay, multiples of 5. Okay, so that means something like 5 and 125. That GCD will be 5. Correct? Hopefully. Okay, so that means 5. And then, of course, when the total, you're going to add 5 plus 5 20 times. So that's going to be 5 times 20, which is 100. Multiples of 25. So that's something like, running out of space here, GCD like 25 and 125. And that GCD, I believe, is 25. So put 25 here, and there's 4 of them, so that's 100. And then the last one, GCD of 125 and 125 is 125. And there's only one of them, so 125. And then, of course, we have to total them all. And when you do, you get 425. So hopefully, the first question that talks about this guy gives you an idea of how to progress with this question once we get to parts B, C, and D. If R and S are different prime numbers, prove that P R squared S is equal to R times 3R minus 2 times 2S minus 1. All right, so before I get into R and S's, it's going to be a bit abstract, right? So I'm going to start with just an example with some numbers. And that hopefully will, be a little bit more digestible. So I'm going to use for R 7. Okay. And I'm just going to calculate P of 7 squared. So instead of R and R squared, I'm just going to calculate P of 7 squared. So you have same kind of story. You have a whole bunch of non-multiples of 7. Then you have multiples of 7, which are 7, 14, 21, 28, 35, 42, and 49. And then you have multiples of 49, 7 squared, which is just 49. So the GCD of the non-multiples, so if this is the non-multiple and 49, all of those will be 1. So for example, I don't know, 9, for example, is a non-multiple. And how many of these guys, we'll make a little table again. We have the number, the GCD, and then the total, just like before. And then we have non-multiple. Okay. All right, so how many non-multiples do we have? Well, these are the multiples. And there's 7 of those guys, and there's 49 numbers, so I believe that would be 42. Yeah, 42. And each of those GCDs is 1, so this is 42. Okay, so that takes care of that. Multiples of 7. Multiple of 7. How many of there are there? And then, of course, multiple of 7 squared, which is 49. Okay. Well, 49, there's only one of those guys, this guy right here. So I'll put 1 there. The GCD of 49 and 49 is 49. So that's 49. Now, this guy had multiples of 7, but unique multiples of 7. So we have 1, 2, 3, 4, 5, 6. So 6 is the answer. The GCD of any of those, so for example, GCD of, say, 14 and 49, that's going to be 7. And then there's the total will be 6 times 7, so 42. And then you just add these up. And so I believe the total is 133 when you add this guy, this guy, and this guy. So that's just an example. I just did that to give you a feel of how to figure this out. Otherwise, you might get a little confused with R's and S's and all that stuff. Okay? All right. So now let's proceed to R's and S's, and keeping that in mind. Okay, so let's just keep this in the same page. It might help. Okay. So the first thing I'm going to do is write this break it up. And I think they even gave you that in the first part of the question. Let me show it to you right here. That P at A, B is equal to P at A times P at B. So they gave you that, so that's very helpful. So that allows us to sort of break it up there. Okay, and then I'll concentrate on this, and then I'll concentrate on that. So first let's concentrate on this guy, and then we'll do that guy. Well, this guy right here we just did over here, but we did it with numbers. So I'll make a similar table here beside it for a comparison. So a number, a GCD, and total. Okay, so we have non-multiples, non-multiple, multiple of R, and multiple of R squared. Got it? This time we are using letters because we have to figure out P of R squared. Before we had to figure out P of 49, which is 7 squared. Okay, so non-multiples, we got to fill this table out now. Okay, shouldn't be too big of a deal. Well, let's start with this one. This is the easiest. There's only one of these guys, and the GCD is just going to be R squared. So this is R squared. Okay, that's the easiest one. Multiples of R is going to be, the number is R minus 1, and then the GCD is R. So this total will be R times R minus 1. And the non-multiples, so I think it's R squared minus R. And then the GCD is 1. So then this would just be R squared minus R. And then, of course, you add it all up. You add these three. And when you add these three, you get, let's just do it over here. R squared minus R plus R squared minus R. Plus R squared, correct? So that's 3R squared minus 2R. Yeah, so okay, so this guy is 3R squared minus 2R. Okay, we got that. Okay, now let's concentrate on PS. And PS, we didn't actually do that yet, so let me just, do you want me to do it as a number? Sure, what the heck. So let's say S is 7. So it would be the GCD of like 1, 7 plus the GCD of 2, 7, and then dot 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 all the way to the GCD of 7, 7. Yeah, so that looks to me like it will be well, the GCD of 7, 7 is just 7, and then all these other guys is 1, and there's 6 of them, so it'll be 6 times 1. So this is 13. So similarly in that, it looks to me that that's going to be S plus S minus 1 times 1. Yeah. I'm doing this carefully here. Don't want to mess this up. Okay, so let's combine it because we got to multiply it, right? So it's 3R squared minus 2R. And then this looks to me like 2S minus 1. And what are we trying to prove here? We're trying to prove, oh, it's right there, right here. I think I have it. I just have to factor out the R. Okay, I got it. So if I factor out the R, it looks just like that. There, I just did it. Okay, great. So I proved it. Part C. If R and S are different prime numbers, prove that P R squared S can never be equal to a power of a prime number. That is, it can never be equal to t to the power of n for some prime t and some positive integer n. Okay, so in order to prove this, first let me see if I can do it. And if I can't, then I will have proven that it cannot be done. Okay. So this part here, we've already kind of been told that it's equal to that. We proved that too. So I'm going to put that in there. And that is equal to t to the power of n. Okay. Now, if you look at this equation, on the right side, it's t to the power of n. And on the left side, you have all these letters. Now, each of these guys must be a power of t. So must be a power of t in order for this to work. So that means that this first guy r has got to be t something. Let's just say it's t. I think that's pretty reasonable to assume. And then let's work through with the other guys and see what happens. So the next guy, which is this one, 3r minus 2, I don't know what that is, so it'll be 2, so let's say it's t to the power of a. And this next guy here, 2s minus 1, let's say t to the power of b. Okay, and let's see what we can get. All right. So this equation here, if I use the fact that r is equal to t, becomes 3t minus 2 is equal to t to the power of a. And then now I've got to figure out what a is. So I got multiple steps here. If a is 1, then this becomes 3t minus 2 is t, and therefore that becomes 2t is equal to 2, so t is 1. Now, they have told me that t is a prime number, so since 1 is not prime, this doesn't work, so I got to keep going here. Let's try a equals 2 this time and see what happens. Then this equation becomes 3t minus 2 is equal to t squared, and therefore this becomes t squared minus 3t plus 2 is equal to 0. And when they factor this, I get t and t, 2 and 1 minus minus. So t is equal to 2 or 1. And since t is a prime number, the only solution here is that t is equal to 2. Because 2 is the only one that's a prime number. Okay, we're getting somewhere, I think. Okay, so now that I've got this t equals 2, let's see if the other things jive. I've got to come back and look at the other parties. I got this one, but what about this one here? So if t is 2, then that means that I've got a scenario of 2s minus 1 is equal to 2 to the power of something. But this falls apart because 2s minus 1 is by definition an odd number on the left side of that equation. And 2 to the power of b by definition is an even number. Any power of 2 is going to be even. So this falls apart. Not possible, I guess, is what I'll write. Okay, so I've proven that it's not possible for t equals 1, obviously, because 1 is not even a prime, and t has to be prime. And I've also proven that when t is 2, which is a prime number, it's not possible because this thing falls apart right here. Okay, great. So, but what about values, different values? Like, for example, when this a is greater than 2, so like, for example, we have this 3r minus 2 is equal to t to the power of a. What about if a is greater than 2, and then we also have, when we substitute r equals t, we have 3t minus 2 is equal to t to the power of a. And what about if t is greater than 2, right? Because we stopped at 2. We have to look at those scenarios. Okay, let's look at those scenarios, see what we get. If my a is greater than 2, then that means that this t to the power of a would be greater than t to the power of 2, obviously. And if t is greater than 2, then that means that this equation that we got over here, this guy right here, t squared minus 3t plus 2, which factors to t minus 2 and t minus 1, that guy, if t is greater than 2, would be greater than 0. So that means that t squared minus 3t plus 2 would be greater than 0. So t squared would be greater than 3t minus 2. So therefore I can conclude that if a is greater than 2, that t to the a is greater than t squared, which is up here. And in t squared from here is greater than 3t minus 2. So that basically means that t to the power of a is greater than 3t minus 2. And therefore t to the power of a could not be equal to 3t minus 2. So this equation up here, which was this one right here, this initial one, cannot be true. That or this equation right here cannot be true, because t to the a will not be equal to 3t minus 2, and we want it to be equal to. So hopefully that made sense. I didn't want it to become too complicated. I tried to explain it as simple as possible. So that basically means that the only value of 2 that works, the only value of t that works is 2. It is the only solution. But that only solution fell apart. When we got it, we had to plug it back into this guy here. And when we did, it fell apart, because then here one side is odd and the other side is even. So that's about as best I can explain it without going through too much pain. And we have finally determined with justification 2 possible integers m for which p of m is equal to 243. All right, here we go. So p of m is equal to 243. And they want 2 possible values. Okay. Well, the first thing I'm going to do is, let's see, 243 is what? 3 to the power of 5, right? So that's going to be the first part. And I'm going to break up this m into, I'm going to break it up into, like, I'm going to let m equal rs, so that way. And then once you break it up into rs, we can use some of the formulas that we have previously been told. So this becomes PRS, and then from part B of this question, if you go back and look at part B, we had already figured out that this would be 2r minus 1 times 2s minus 1. Got it? So that's going to be very helpful for us. So we now have this 243 up here, and we have this 2r minus 1 and 2s minus 1. Okay. 2s minus 1. All right, so that's pretty good progress here. And let's make a table and see what happens. So I've got 2r minus 1, 2s minus 1, and then r, and then s, and see what values we get. Okay, so we want this times this to equal 243. Okay. Is there any parameters here? They're both positive integers, I guess. Well, m is a positive integer, and that's all we know. They're obviously going to be... Oh, I got it. These, based on our on this question, the definition in the question is that r and s are prime. R and s are prime. Right? Is that right? Let's go back and see this question here. You can use this, but different prime numbers. Yeah. It's all prime. Okay. All right, so let's just concentrate on that. Okay, so that means that these two guys have to eventually be prime. Not this and this, but those two, R and S, have to be prime. Okay. All right, so let's first figure this out. There's lots of combinations, but I'm just going to write a couple. 81 and 3, that will multiply to give 243, like if this was 3 and this was 81. 9 and 27. And then the other ones are sort of the same. What I mean by that is like they become like interchangeable. And there's 1 and 243 also. Yeah, I think so, right? 1 and 243. Okay, so let's figure this out. So 2r minus 1 is 1. That means 2r is equal to 2, so r is 1. So if that's the case, then this is invalid because r and s have to be prime and 1 is not prime. Okay, so let's look at the next one, 3 and 81. So if 2r minus 1 is 3, that means 2r is 4, r is 2. Okay, so far so good. And then 2s minus 1 is 81. So 2s is equal to 82. Therefore, s is 41. Okay, is 41 a prime? I believe it is. Okay, let's look at the next one. And, well, I'll let you figure it out. It's 5 and 14. You got to do some math. And then this is not a prime, so this falls apart. So the only one that works is 2 and 41. Right. So that means that our only solution is P of RS, which R is 2 and P is 40. R is 2 and S is 41. And that's 243. And therefore, when you do this math, it's P of 81 is 243. So my first value of M is 82, right? Oh, sorry. Yeah, this should be 82. Sorry about that. My math. 2 times 41 is 82. I gotta make sure I get that right. So our first value is 82. And they want 2 possible. Okay, so there's obviously one more. Okay, so here we go. We gotta do the same thing, but we gotta do a different technique this time. So this time, I'm gonna try PR squared S and see if that equals 243. Now from part C, if you remember part C, let's go back and read it again. It says that PR squared S can never be equal to the power of a prime number. We proved that. It can never be equal. So that basically means that this thing will not be possible because P to the power 2 to the power of 243 is a power of a prime number. It's 3 to the power of 5, right? Okay, so that falls apart. We can't use that. So how do we get another value for M? I guess we have to keep extrapolating here. We gotta now look at how about P R to the power of 3s. Let's see if that equals 243. Okay. If that's the case, then we have to figure out a formula for this. All right, we got to figure out a formula. And, oh boy. I'm going to first, again, do it with numbers, and then I'll do it with letters. So, PR to the power of S, PR to the power of 3s. First, we'll break it up into PR cubed PS. The PS part, that one, you know, that's just, I believe, what was it? Was it 2s minus 1, right? Yeah, 2s minus 1. But this guy, that's what we have to figure out. That's going to be the big one. But the good news is if we can figure it out, then we can do this question. All right. So first, let me just give you an example. Instead of using r's, it might be a little too abstract, I'm going to use a number. I'm just going to use 3. And then we'll try to figure out. So for powers of 3, we got 3, or not powers of 3, multiples of 3. 3, 6, 9, 12, 15, 18, 21, 24, 27, right? Okay. So let's make a little table here. Just like before. Number, GCD, total. And then multiple of 3 to the power of 3. Multiple of 3 to the power of 2, which is 9. Multiple of 3. And then non-multiples. Okay. All right, let's see what we get. And let's try to figure this out. Okay, so multiples of 27, there's only one of those guys. It's just 27. And the GCD of 27 and 27, I believe, is 27. Yes. So therefore, this total would be 27. Okay, so that's pretty straightforward. We took care of this guy. Multiples of 9 are 9 and 18. Now, unique multiples, because you can't include 27 again. So that's 2. Okay. The GCD of like a 9 and a 27 would be just 9, I believe. Yeah, so 9. So then this becomes 18. Multiples of 3. So we have 1, 2, 3, 4, 5, 6. So unique, the ones that we haven't counted yet. So 6 here. The GCD of like a 3 and a 27 would be 3. So this is 18. And then non-multiples, well, there's 27 numbers in total. We already included 1, 2, and 6, so we've already counted 9, so there's 18 left. And those GCDs are all 1, so this will be 18. So this total, well, whatever it is, it doesn't really matter. I'm just giving an example, but you got to total it all up. Now I will turn my attention to this guy, the R, because the R is what we're interested in. The R is what we have to put right here. Okay, so let's do the same thing. But this time we'll use R. So total, GCD, number, and then we got the same story here. What do we have? Multiple of R cubed, multiple of R squared, multiple of R, and non-multiple. Correct. Okay. So multiple of R, there's only one of those guys, and the GCD will be R to the power of 3, so therefore this is R to the power of 3. Okay? You can kind of look at this guy here to get a understanding of how this, and that's why I did the example with the numbers, because otherwise it may not be as obvious. Okay, so let's keep going here. So multiple of R squared, there's R minus 1 of those guys, and each GCD is R squared, so this will be R minus 1 times R squared. That total. Multiples of R, there's R squared minus R of those guys, and each of those GCDs is R, so this will be R squared minus R times R. Non-multiples are R to the power of 3 minus R squared. Each of those GCDs is 1, so this will just be R squared. R cubed minus R squared. All right, and now to get the total, of course, we've got to add all these guys. So we have to add these guys, and I will let you add it up. I'm sure you can do that. I'm sure you can do that algebra. And when you do that algebra, you get 4R cubed minus 3R squared, and that is what I put in here: 4R cubed minus 3R squared. Okay, so big long song and dance to get that formula, because that formula was not given to us. We have to calculate it. Okay, so now let's use that formula. This guy. Okay, so what do we do now? We have to figure out what are we trying to figure out here again? Oh yeah, possible values. Okay, so this shouldn't be too bad now. So basically what that means is we have a situation where 4R cubed minus 3R squared is times this 2S minus 1 is equal to this guy, which is 243. So let's squeeze that in there, is 243. Now 243 is 3 to the power of 5. And then from this guy, I'm going to factor out an R squared, and that will leave me with 4R minus 3, and then this is just 2S minus 1. Okay, so just look at that for a second, and when I think about it, R can only be 3. It's our only choice here. That's the only way this is going to work, because all of these three factors have to be multiples or powers of 3. So R equals 3 is our only choice. If that is the case, then that becomes 3 squared, 4 times 3 minus 3 times 2S minus 1 is 3 to the power of 5. So that's great, because this is 9, this is 9, This is 2s minus 1 is 243. And when you solve for s, you actually get s is equal to 2. Okay, great. So that means that PR cubed s is really P3 cubed times 2, which is P54. And that gives you your second value of m, which is 54. And there you go. 54 is our second value, and up here we got 82 as our first value.